In this video, we're going to talk about the rules for nomenclature. So our rules for nomenclature have been established by this organization called IUPAC, the International Union of Pure and Applied Chemistry, IUPAC. And they basically establish the rules for naming inorganic compounds, organic compounds, and pretty much anything chemistry related. So that's what we're learning today is IUPAC nomenclature rules. So most inorganic compounds do not contain the element carbon. One thing that we talked about early in the course is that there's an entire field of chemistry called organic chemistry, where it's primarily compounds containing carbon and then as well hydrogen and oxygen. So we're learning the nomenclature rules for inorganic compounds. A couple exceptions that they mention, carbon dioxide and then the carbonate ion. These obviously contain carbon, but they're still going to follow the same rules. Now there's 5 types of compounds, classes of compounds that we're going to go over. So first we're going to explain what makes each one. So binary ionic, ternary ionic, binary molecular, binary acid, and ternary oxyacid. We're going to explain each one of these, and then we're going to go through the rules for each one of these and do examples. So here's a flow chart. In short, we essentially have 3 different sets of rules. We have rules for ionic compounds and rules for molecular compounds where it's a nonmetal bonded to another nonmetal. And then we also have some rules or patterns for naming acids, and we're going to go through all 3 of these right now. So by binary ionic compound, what we mean is an ionic compound that contains only 2 elements. So for example, here we have sodium and chloride. Here we have aluminum and chloride. Because we've just have 2 elements, we're calling them binary. And because it's a metal bonded with a nonmetal in both of these examples, it's ionic. Next group, a ternary ionic compound. So we've got 3. We've got, for example, here potassium, nitrogen, and oxygen. And then in this other example, we have aluminum, nitrogen, and oxygen. So we have 3 elements here. So that's why they're called ternary. And these are still ionic because, and we'll see this in this lecture, but we've got a metal right here, the potassium, and then this NO3, this is what's called a polyatomic ion. But recall nitrogen and oxygen are both nonmetals. So it's like we still have a metal bonded to a nonmetal, which is why it's ionic. Next, the binary molecular compounds. So this is when you're going to have 2 elements, but they're both nonmetals. So 2 elements, like here we have nitrogen and hydrogen. Here it's hydrogen and oxygen. It's 2 elements, that's why it's binary. And then molecular, because we're talking about both of the elements are nonmetals. So when you have 2 nonmetals bonded together, you're going to get a covalent bonding relationship, and we'll call those molecules. So technically it's not correct to call something like sodium chloride a molecule because it doesn't have a covalent bond in there, it has an ionic bond. Next for the acids, so binary acid, as you might guess, we've got 2 elements. So for example, hydrogen and chlorine, we have 2 elements, so binary, and hydrogen and chlorine makes hydrochloric acid. Again, we're going to learn the rules for this on how we got that name, but it is an acid, so that's why we're calling it binary acid, and it kind of has its own rules or its own pattern for naming that we're going to review and observe that pattern. And then ternary, as you might have guessed, we have 3 elements, so hydrogen, nitrogen, and oxygen. We have 3 elements, and oxyacid, because all of these examples that we're going to see, they have oxygen as one of those 3 elements. So they all contain hydrogen, oxygen, and one other nonmetal. In this example, just a fun fact about hydrofluoric acid, it's considered a weak acid, but in extremely high concentrations like we have on the bottle here, it will dissolve your bones, and it's pretty scary stuff. That's just an interesting fact. Okay, so reviewing some terms, because I do believe we have mentioned these terms once at least before, at least these first ones. So an ion is any atom, or it can be a group of atoms with a charge. So if it's a neutral element, it's just an atom, but as soon as it loses or gains electrons, we call it an ion. If it happens to be positively charged, we're going to call it a cation, not cation, but cation. And if it's negatively charged, we're going to call it an anion. And then if we have several atoms together and that group of atoms has an overall net charge, we're going to call it a polyatomic ion or polyatomic anion. So most of the polyatomics happen to be negatively charged, so that's why they have anion here, but there actually is one that you're going to need to memorize that happens to be positively charged, so it would be a polyatomic cation. But generally, we just refer to them as the polyatomic ions. But they're anytime you have a group of atoms. So some examples, NO3 with a minus charge, we're saying that the nitrogen and the 3 oxygens all together collectively have a 1 minus charge, so that's a polyatomic ion. Another one, PO4 with a 3 minus charge, so it's 1 phosphorus and 4 oxygens. Collectively, those 5 atoms together when bonded with a 3 minus charge, that has its own special name. That's another example of a polyatomic ion. Poly, obviously, for many atoms. So just another flow chart. So in general, with ions, you have positive ions and negative ions, and in both cases, they can be a single element. So a positively charged monatomic ion would be like sodium, and an example of a monatomic anion would be like chlorine. And then polyatomic, an example of a positively charged polyatomic would be, for example, NH4+, that happens to be called ammonium. And then an example of a polyatomic anion, we can do the NO3, for example. Again, that one happens to be called nitrate, but that's just the general grouping we have. Positive ions, negative ions, and then in both cases, they can be a single element or a group of elements, single or a group. So recall that metal atoms are going to lose valence electrons. So therefore, they're going to become positively charged because electrons, remember, are negatively charged. If an atom loses negatively charged, then the overall charge of the atom must be positive. So the point is that metals become positively charged. So we're going to use the word cation again for positive. Now, how we actually name them, we just pretty much do the name of the element followed by the word ion. So Na+, we're just going to call it sodium ion. Mg2+, this is magnesium, we'll just call it magnesium ion. So just naming the ions themselves is pretty straightforward. Now with this bullet point, they're saying this rule applies for metals that usually form one ion. So the rule they're talking about is just saying the name of the element followed by the word ion. We're pretty much going to do that for all metals. However, there's a few, for example, all of the transition metals, they can form different charges. So we're going to have another rule on the next slide. Now, this rule applies to metals that form one ion. So for example, that would be group 1s, group 2s, and then we have a few others, so like silver, zinc, and cadmium. If you take a look at your periodic table, these 3 are in the transition metals. So you might think that they could have multiple charges based on what we learned today in this lecture, but it turns out that silver, zinc, and cadmium pretty much always form a +1, a +2, and a +2. So we're not going to use the next rule, basically this rule that's on this slide, this Roman numeral thing, is not going to be used for these 3 because it's simply not necessary. But let's clarify what we mean by the Roman numeral thing. So if a metal can form more than one cation, so if it can be +1 or +2, or it could be +2 or +4, depending on what it's bonded with, what day of the week it is, then we're going to use Roman numerals to clarify what the charge is on the ion. So this one here, it would be incorrect to simply say the copper ion, because copper can be +1 or +2. So what we do is we add Roman numerals in parentheses to clarify what is the charge on the metal atom or the metal ion. So this one we would call the copper 1 ion, and this one we would call the copper 2 ion. If we had one that was, here's another example, so Pb and then a Roman numeral IV, so this is for a +4, and then say it was bonded with 4 chlorines, for example, which how I got this is actually not really written correctly, but I just wanted to show you as an example. Pb is lead, IV in Roman numerals is 4, so this would be the lead 4 ion. Or we could say lead 4 chloride, but lead 4 is referring to Pb, and then it's saying that it's a lead with a +4 charge. And just to clarify, what I wrote here is really, really not correct at all. I was just trying to write something for the sake of giving another example. This is correct. How I wrote the name here is correct. Anyway, there's another naming system that's not too common. This is called the Latin system, but we might see, and for example, they're using copper again, but you might see these alternate endings on the names when you've got two different metals or two different charges that a metal can have. So with the copper, for example, we had copper 1 and copper 2. You might see, instead of it being called copper 1, it's called cuprous. And instead of the copper 2 being called copper 2, it's called cupric. So this is something that you might see if you take more chemistry classes and, for example, you have access to a stock room and you need to get chemicals off the shelf. If you see something called cuprous such and such or cupric such and such, it's referring to the charge. Now, it's not used very often. We more often will use the Roman numerals, which is called the stock system. But just keep in mind that this is a thing. You might see it, you may not. But it's just basically adding OUS or IC to the ending. Another example might be for iron, it's actually ferrous and ferric. So remember, the symbol for iron is Fe. That's where the fer comes from. I don't know, I think it's Latin, I have to double check, but the point is you have that OUS and that IC as well. Just another example of something where it might come up. So then we just talked about metals, now going to nonmetals. Nonmetals, recall they will gain electrons, and since electrons are negatively charged, if an atom gains an electron, then it's going to become a negatively charged ion, which again we call an anion. And then the naming here, it's a new rule. So with metals, we just said the name of the element plus the word ion, like sodium ion, magnesium ion, barium ion. Here, for nonmetals, we're going to actually change the name of the element by adding an IDE ending. So for example, bromine, instead of bromine, it's called bromide. Instead of chlorine ion, it's called chloride. Fluorine is fluoride. Iodine is now called iodide. Nitrogen is nitride. Oxygen is oxide. Phosphorus is phosphide. Sulfur is sulfide, and so on. Now, the word ion is almost optional because honestly, if I said nitride, the ID ending is telling the listener that I am talking about the nitrogen ion. So having the word ion is almost not necessary, but the IDE ending, that is the critical part for this nomenclature rule. So then we're going to go into predicting formulas. So we just talked about how do we name the individual ions for metals and nonmetals, and now we're going to put them together to actually get formulas. So just a couple things to remember. Group 1, so group 1 and group 2 metals are always going to be +1 and +2 respectively. So group 1 metals, that's that very first column on the far left of the periodic table, and examples include sodium, lithium, potassium. Those are always going to be +1. And then group 2s, those are always going to be +2. So examples, we have magnesium 2+ and calcium 2+, and I think barium's in that list as well, but those are always going to be 2+ ions. And then they've call it group 13 over here, but it's basically that aluminum column. Those are always going to be +3. And then in the middle, basically with the transition metals, you have those metals can pretty much be anything. They can be +1, +2, +3, +4. You could get +5 and +6 and so on. It's somewhat predictable. One thing you can do is look it up on Wikipedia, and then the charges that are in bold are usually the most common ones. But the point is the transition metals, they're not always the same thing. So that's why we're going to use the Roman numerals. So we do not use Roman numerals when the charge is predictable, like with these first 2 bullet points. But when the charge is not predictable, like with the transition metals, that's when we're going to use the Roman numerals. The Roman numerals in the name anyway. And then how we speak the name and how we write the name on paper. So nonmetals gain electrons to form anions in a predictable fashion. So that's good to hear. So these are all the halogens, for example. Those are all going to be -1. And recall the reason for that is because if a halogen, like fluorine, gains one single electron, then it will have a complete outer shell, and we say it's more stable. So that's why the halogens gain just a single electron. So you know that all of those elements in group 17, those halogens, they're always going to be 1-. And then the column next to that, so the oxygen group, those are always all going to be 2-. And then the group next to those, so nitrogen and phosphorus, those are all going to be 3-. So this is going to be predictable. These nonmetals will always be the charge based on their column, 1-, 2-, or 3-. So here's just kind of like a summary. And you should try to at least memorize, you don't have to memorize this grouping here. I would recommend you memorize these 3 metals, the silver, cadmium, and zinc, because they're kind of like exceptions. So this block in the middle, this is your transition metals, and they are not predictable, as in like they could be 2+ or 3+, or here's 1 and 2+. Mercury can be 1 or 2. This one's actually a very interesting exception that I don't want you guys to worry about. But this grouping and these groupings here, so you really need to try and memorize the fact that, metals in group 1, they're always going to be +1. Metals in group 2, those are all going to be +2. Hydrogen's always +1. And then these 3 over here, make sure you have that memorized. And also aluminum. Aluminum is always the +3. So then now we're going to talk about polyatomics. So this said polyatomics up here. I really shouldn't have said that. But polyatomic ions, again, this is going to be multiple atoms together where the whole group of the atoms has a charge. So an example that I had earlier, NO3 with a 1- charge, we called that nitrate. Here's another example that I didn't put earlier. So SO4 with a 2- charge, that's called sulfate. So these are just examples of polyatomics, but they contain one or more elements that are combined, and they're combined covalently. So the NO3, those are all covalently bonded together, and you typically have oxygen in with these, so that's why they're calling them oxyanions. And a lot of them have this ATE ending, but some of them also have an ITE ending, and we're going to look at the pattern for that on this slide. So some oxyanions have ite. So we had 2 examples here. We had nitrate and sulfate. Here we've got nitrite and sulfite. And notice that the formula is different. So the ATE sisters, if you will, of this one, look, this is NO3, this one's NO2. This is the pattern that we want you to observe. The sulfate, where it's ATE ending, this is SO4, and then the ITE is SO3. So these oxyanions, the ITE ending ones, they have 1 less oxygen than the ATE ones. So that's the pattern we want you to notice, is that when you've got a pair of polyatomic ions that are clearly very similar, but one is ending in ate and one's ending in ite, the difference is 1 less oxygen. So if the ate is like, XO3 with a 2- charge, I'm just making up an example, then the ITE must be XO2 with a 2- charge. We just basically took away 1 oxygen. That's the pattern. So the names are not arbitrary. There is some sort of rhyme and reason to all this. So they have 1 less oxygen. And we've got a nice summary on one of these slides. We've got a table, another table that I'm going to have that basically you need to memorize. But here's another example. So with regards to chlorine, so chlorate is ClO3. So then using the rule we just learned, what would chlorite be? So Cl, and then 1 less oxygen, so O2, and then the minus charge stays the same. So notice that the charge does not change when the number of oxygen atoms changes. So that we just saw that same pattern with the nitrate and nitrite and the sulfate and sulfite. The charge stayed the same. So with nitrogen, it happened to be a 1-. With the sulfur, it happened to be a 2-. So the charge is not what's changing, it's just the number of oxygens that changes. So with chlorine, chloride is the ClO2. Now, I wouldn't call these exceptions, these just happen to be their names, but the point is that these two in the list of polyatomic ions that you are going to have to memorize, these do not use the ATE or ITE ending, but it's still important to know them. So hydroxide is really, really important. When we start talking about acids and bases, we're going to talk about hydroxide quite often. Cyanide, not as common, but it's another example where we're using IDE ending. Now, one bit of confusion, and I apologize for this, but we're using the IDE again. So remember with the nonmetals, when it goes from an atom to an ion. So for example, bromine becomes bromide. So there's that IDE ending. Here's the IDE ending again, but this is cyanide. So there is no element called like cyanine, and there is no element called hydroxine or anything like that. So you'll just have to recognize that hydroxide is specifically referring to OH minus, and cyanide is referring to the CN minus. You just have to memorize those formulas. That's what we tell the students. This is one of the few things in chemistry where you just have to simply memorize it. I suggest you make some flashcards or something. But otherwise, most of the stuff in chemistry, you don't really have to memorize too much because it all kind of makes sense. There's a logical reasoning for why we do things the way we do. Anyway, here's a table. Again, flashcards. Highly recommend you make flashcards to try and memorize these. But we can observe our patterns. So like here is the chlorines with the ate and the ite. And then here's the nitrogens with the ate and the ite. We've also got the chlorine. I don't think they put the chlorine ones on there, but we've got hypochlorite, and then ClO2 minus would be called chlorite, and then ClO3 minus would be chlorate, and then ClO4 minus would be called perchlorate. Oh, here's this perchlorate one. But basically try to memorize these. One interesting, could be like an exam question, a good exam question. We've got phosphate. I could ask you, what would be the formula for phosphite? So phosphite with an ITE ending, you should be able to deduce what the formula is based on the rules we just learned. So instead of PO4, it should be PO3, and the charge doesn't change, so it's 3 minus. And then here is our single positively charged polyatomic ion. So you've noticed that most of them are negatively charged. We do have one that's positive. It's pretty common, so don't neglect this one, but ammonium, which is different from ammonia. So ammonia is something you can buy from the store. Cleaning agent, it's NH3. This one is ammonium, where it's NH4 with a positive charge. So make sure that I would suggest maybe make a flashcard for this one just so you can learn the difference between those two. You memorize the difference between those two, NH4 plus and NH3, ammonia and ammonium.